Hi guys, and welcome to this virtual lecture course on Classical Mechanics and Relativity. I'm Dr. Andrew Mitchell, and in this lecture we'll be deriving the Lorentz transformations of special relativity. In the previous lecture, I introduced the concept of special relativity, and we saw how the constant speed of light in all inertial reference frames, as predicted from Maxwell's equations, and established as an experimental fact in the Michelson-Morley experiment, is actually inconsistent with Newtonian physics. In particular, it's inconsistent with the Galilean transformation between inertial reference frames. Einstein took as a postulate, just a law of nature itself, that the speed of light is constant. He also took the principle of relativity and elevated it to describe all laws of nature, not just mechanics. In this lecture, we will take these two postulates and from scratch build up the Lorentz transformations. These generalize from the usual Galilean transformations at non-relativistic speeds to the situation when we are talking about relative velocities which are large compared with the speed of light. We will see that these transformations scramble up space and time in a non-trivial way, and we'll explore some of the consequences of that. This breaks down our idea of simultaneity as being an absolute. We will see the relativity of simultaneity, meaning that events that occur simultaneously to me might not occur simultaneously to you. All of this comes out from the Lorentz transformations, and that's going to be the topic of today's lecture. So let's get down to work.
Einstein elevated the constant speed of light in all reference frames to be a law of nature itself, a postulate of his theory of special relativity that was taken as fact and required no a priori justification. The Michelson-Morley experiment that we discussed in the previous lecture, however, seemed to really establish this as an experimental fact, and indeed other experiments confirmed the result. In addition, Einstein believed that Maxwell's equations, describing light as an electromagnetic phenomena, were correct. He thought they were too beautiful and elegant to be wrong, and he believed Maxwell's equations were themselves laws of nature. The principle of relativity was also taken to be a postulate, but going further than Galileo and Newton, Einstein postulated that relativity applies to all physical laws, not just to mechanics, but also to electromagnetism and everything else. It is, in a sense, a meta-law, a law governing all the other laws. In 1905, Einstein used the following postulates to derive his special theory of relativity. The first postulate was the principle of relativity itself, that the laws of nature and all of physics is the same in all inertial reference frames. No reference frame is preferred, and there is no such thing as an absolute velocity, or in fact an absolute anything. Everything is supposed to be relative. This is very similar to the principle of relativity known by Galileo and Newton, except Einstein has elevated it to all laws of nature rather than just mechanics. However, the important thing is that Einstein supplemented this by a new postulate, the constant speed of light, that in vacuum, light travels with the same constant speed, c, in all inertial reference frames. In fact, as we'll see, this is all he needed to derive the special theory of relativity. However, to do that, he really had to go right back to basics and examine carefully from scratch all of the assumptions that had gone unquestioned for so many years in the formulation of Newtonian mechanics. Einstein re-derived classical mechanics from its fundamentals, taking care this time to avoid any assumptions beyond the above two postulates. In particular, we'll see that we have to be much more careful and precise about what we mean by lengths, times, and the very concept of simultaneity. These turn out to be reference frame dependent. Only the speed of light is a constant in all frames. That's really the only thing that we can depend on to be the same in all reference frames, and Einstein made very good use of that fact to derive his special theory. The story starts with the concept of simultaneity. What does it mean for two events to be simultaneous? Well, if two events are simultaneous, then obviously they occur at the same time. But how do we know they occur at the same time if they are separated in space? We can't be at both positions at once to check. Well, we can just look at the clock. But then, this requires to synchronize our clocks that might be at different positions in space. So the question now becomes, how do we synchronize distant clocks? Einstein suggested the following thought experiment which establishes a protocol for synchronizing two clocks based on light signals. Why? Well, light signals are the only thing that we can trust to travel at the same speed c in all reference frames. And this gives rise to the idea of a light clock. Einstein suggested the following. Imagine two people, traditionally called Alice and Bob, separated in space by a distance 2d. Let's say this is along the x-axis, and the coordinate xa of Alice is set to be the origin x equals 0. The x-coordinate of Bob is therefore at a position 2d. Now, halfway between, we place Charlie. So he is a distance d from Alice, and a distance d from Bob. And of course, therefore, his x-coordinate xc is equal to d. How do we know that Charlie is exactly halfway between Alice and Bob? Well, we can use meter sticks to measure. We physically measure the distance, and we see that the distance from Alice to Charlie is the same as the distance from Charlie to Bob. Now, Alice and Bob agree to send out a flash of light at exactly 12 noon. And when I say 12 noon, I mean 12 noon according to their own watch. Alice has a watch, and we'll call the time 12 noon according to her watch TA equals 0. Bob also has a watch, and 12 noon for his watch corresponds, let's say, to TB equals 0. What we wish to do is synchronize the clocks for Alice and Bob so that TA equals 0 and TB equals 0 correspond to the same time. So why do we use light signals to synchronize the clocks? Because it takes the same amount of time for light to travel the distance d in any reference frame. The time for light to travel to Charlie from Alice is a time d over c. It's a distance d divided by the speed of light c. But of course this is exactly the same amount of time it takes for light to travel from Bob to Charlie, since the distance is the same and the speed of light is the same. Importantly, if Alice and Bob's watches are synchronized, and given that the travel time for the light is equal in both cases, then the light will arrive at Charlie at the same instant. If the light arrives at Charlie at the same instant, then we know that Alice and Bob's watches were synchronized. Let's draw this on a space-time diagram to see more clearly what's going on. Here is a space-time diagram in which I plot the x-coordinate along the horizontal axis, and then c times t along the vertical axis. The reasons for the choice of c times t here we discussed in the last lecture. It's basically so x and ct both have units of length, and also to ensure that light rays appear as 45-degree lines. I've marked on the x-axis here the position of Alice at the origin, and Bob at a position 2d, as well as Charlie halfway between. Now, at t equals 0, Alice fires her light ray out from the origin. That's this blue line. It starts off at x equals 0, at t equals 0, and it propagates along the x-axis. We can write that the position of the light is at x is equal to c times t. Hence we have this 45-degree line on the spacetime diagram. Also at t equals 0, Bob fires his flash of light, but in the opposite direction. At time t equals 0, the light is at a position 2d, and therefore x is equal to 2d minus ct. The light is still travelling with a speed c, but in the opposite direction. The whole point of this light clock is that Charlie will receive these two flashes of light at the halfway point, at exactly the same instant in time, this is the crossing point of these two lines, if Alice and Bob's clocks are synchronized. And we can see that on the diagram by just dropping this perpendicular, and we see that indeed the crossing point of the two light rays is exactly at the halfway point where Charlie is located. The time it takes for the light to arrive is this time here, which is delta t equals the distance d over c. So if light rays reach c at the same instant, then A and B have synchronized clocks. They sent their signals simultaneously. In particular, note that simultaneous events are connected by horizontal lines on the diagram. What I mean by this is that Alice and Bob sent off their light rays at exactly the same instant, and that means that they occur at the same point on the vertical axis. They're connected by a horizontal line, which in this case is the x-axis itself. But if I looked at any other pair of events on this diagram, providing they are connected by a horizontal line, that means that they occur at the same time. They are simultaneous. Why? Because simultaneous events in this reference frame means that events occur at the same t. They're at the same horizontal line, parallel to the x-axis, perpendicular to the t-axis. Now, it might seem that I'm labouring these very, very simple points, but as we'll see in relativity, we really have to be very careful of exactly what we mean by these terms, so that we can identify the breakdown in the classical Newtonian way of looking at things when we incorporate the new postulate of the constant speed of light. The next step is to consider what all of this looks like to an observer that is moving relative to Alice and Bob. In particular, let's say that Charlie is now moving with a fixed speed v relative to Alice and Bob along the x-axis. Here I've drawn on in the black line the position of Charlie as a function of time. His x-coordinate along this line is x is equal to v times t, plus his initial starting point at d. So, at noon, according to their now properly synchronized clocks, Alice and Bob send off their light signals to the centre, where Charlie is positioned. But the light does not arrive at noon, since the light travels with a finite, rather than infinite, speed. The light arrives at the midpoint sometime later, delta t equals d over c, as we saw earlier. But by then, Charlie has moved to the right slightly by an amount delta x is equal to v delta t. So Charlie sees the flash of light from Bob before the flash of light from Alice. Why? Because he's closer to Bob than Alice when the light reaches him. So how does all of this look from Charlie's perspective? Well, at t equals 0, he starts off at the midpoint between Alice and Bob. We know that because they get out their meter sticks and they measure the distance. At a later time, let's call it t1, Charlie sees a flash of light arrive from Bob. But there's no flash of light from Alice yet. He has to wait till a time t2 before Alice's light arrives. So the light arrives at Charlie at different times. Charlie can either say that the clocks were not synchronized, or he can say that the meaning of simultaneity is simply different in different reference frames. The light signals must not have been sent simultaneously, given that the light arrived at different times. This is the philosophy adopted by Einstein. But this now begs the question, what are simultaneous events to the moving observer? What would Charlie judge to be simultaneous events? So let's call the rest frame of Alice and Bob reference frame S. Simultaneous events in reference frame S have the same t. In particular, t equals 0 is just the horizontal axis. The question is, how does all of this look to a moving observer? Charlie is in reference frame S primed, moving with a speed v relative to S. For the moving observer, simultaneous events have the same t primed. To understand this, we need to redraw our diagram. So this is my spacetime diagram drawn again in the reference frame S. What I mean by that is that Alice and Bob are in the reference frame S, and I'm drawing coordinate axes here, x and ct, in the reference frame S. At t equals 0, we know that Alice and Bob are exactly 2d apart. Indeed, at t equals 0, Charlie is halfway between them, so I can write on the diagram that this is a distance d, and this is a distance d, along the x-axis of reference frame S. Now I'm going to draw on the position of Charlie. He's moving with a velocity v relative to reference frame S, so I'll draw his position on the diagram. This line is his position, x is equal to vt plus d. These are distances measured in reference frame S. If we consider reference frame S primed, the co-moving frame, this is Charlie's rest frame, then he has a coordinate system which moves with him. He can measure, with his meter sticks, distances along the x direction, as he moves along. So I can draw on the same diagram a distance d in the positive x direction in Charlie's rest frame. That would be this line. That is the distance x is equal to vt plus 2d. So this is the line that is always d ahead of Charlie. Likewise, I can draw another line, x is equal to vt, which is always a distance d behind Charlie along the x-axis. So the lines that I've drawn on here are basically the distances relative to Charlie in the moving reference frame S primed. For the moving observer, where is the t primed equals 0 axis? At x equals 0 and t equals 0, we know that x primed is equal to 0 and t primed is equal to 0 because we're in the standard configuration. The coordinate systems match up at t equals 0. But what about a later time? What are simultaneous events to the moving observer? To answer this, we have to ask ourselves, how would we synchronize clocks in the moving frame of reference S primed? Well, again, we use light rays. Light rays must arrive at Charlie at the same instant in time, in his reference frame. So we just have to work backwards. And here we're helped by the fact that light is always travelling at the same speed, independently of the reference frame. So let's say that Alice shoots off her light ray signal at exactly t equals 0. That is also t primed is equal to 0, because both s and s primed coincide at t equals 0. So let me draw on the light ray, starting at the origin here, at Alice's position, at x equals 0 and t equals 0. This light ray will be the usual 45-degree line. In particular, the light arrives at Charlie at this point here, which I'll denote point P. The question now is, what is the event for Bob that is simultaneous with Alice's release of the light ray at t equals 0? Well, in the moving frame of reference S primed, the definition of simultaneity would be that the light rays arrive at Charlie at the same instant of time. That means that in terms of our diagram here, that the light rays from Alice and Bob must intersect at the point P. Bob's light ray is also a 45-degree line on this diagram. So a light ray going in the opposite direction that intersects through point P must be this ray. And you can see here that this must have been released by Bob at this position. Let's call that point Q. So let's just summarize the logic here. Charlie is moving along with a velocity v. Alice sets off her light ray at a time t equals 0 in her reference frame. The question is, what is the time when Bob has to set off his light ray so that the light rays arrive at the same instant in time at Charlie's position? So Alice sets off her light ray, that's this light ray here. It arrives at P at a particular instant in time. Bob must set off his light ray at a different instant in time, that's at point Q, so that the light rays arrive at Charlie at the same instant. That's at point P. Simultaneous events in the moving reference frame S primed are therefore parallel to the line connecting the origin to point Q. They are no longer horizontal lines, as simultaneous events would appear in reference frame S. To understand simultaneous events in reference frame S primed, we simply therefore have to find the spacetime coordinates of the point Q, and this is a simple matter of geometry and algebra which we'll go through now. First of all, we need to work out the spacetime coordinates of the point P. What I mean by that is we need to work out the position, let's call it xp, and also the time at which the event P occurs. Let's call that Tp. Let's also label the origin on the diagram. This is the point O here at x equals 0, t equals 0. So we have a light ray going from the origin to point P. So this light ray, OP, is described by the line x is equal to ct. It's a light ray, after all, travelling with the speed of light. On the other hand, the trajectory of Charlie is described by the line x is equal to vt plus d, as indicated on the diagram. The point P is at the intersect between these two. And what that means is that we just set these lines equal to each other. So xp is equal to ctp at the point P, but that's also equal to vtp plus d. And we can solve that for the time tp. We get that tp is equal to d over c minus v, where d is the initial separation between Alice and Charlie. Plugging tp back into the expression for x, we obtain cd over c minus v. So, very straightforwardly, we've obtained the coordinates of the point P. So what about the coordinates of the point Q? We call those coordinates xq and tq. How do we find them? Well, we have a light ray, qp, which is described by the equation x is equal to minus ct plus some constant. That constant corresponds to whereabouts this light ray intersects with the x-axis. That's something that we're going to have to calculate. However, we can do that by looking at the point P. There we have that xp is equal to minus ctp plus the constant. That's the intersection of the light ray qp at the point P. But of course, we've just worked out the coordinates of the point P, so we can substitute it into this equation. So we obtain this expression, which can be rearranged to find the value of the constant. And that follows simply as 2cd over c minus v. Okay, so we can now plug the value of this constant into this expression for our light ray, and that then defines precisely the light ray from Q to P. Okay, so how are we going to determine the point Q? Well, it's the intersection of the light ray QP with the trajectory of B. And we know the trajectory of B. It is simply x is equal to vt plus 2d. So Q is at the intersection. Meaning that xq is equal to minus ctq plus 2cd upon c minus v, which is likewise equal to v times tq plus 2d. We can now rearrange this expression for tq, and this is what we get. We can tidy this expression up a bit using a bit of algebra to obtain the following. tq reads 2dv over c squared minus v squared. We can now plug this expression back into this equation and obtain the x-coordinate of the point Q, and we obtain that xq is equal to 2dc squared over c squared minus v squared. So we've achieved what we wanted to find out. We've found the coordinates of the point Q. This is the space-time event when Bob must have set off his flashlight so that the signals arrived simultaneously to Charlie in the moving frame of reference S primed. So the coordinates of point Q are xq is equal to 2d squared upon c squared minus v squared, while tq is equal to 2dv over c squared minus v squared. In particular, this implies the following. We can write that c times tq is equal to v over c times xq. I can do that because there's quite a lot of similarity between these two expressions for xq and tq. This is nice because it allows me to draw on the diagram a line from the origin to the point Q, which is precisely this line. Ct is equal to v over c times x, and at point Q it passes through precisely these coordinates. The green line that I've drawn on here is a line connecting simultaneous events in the moving reference frame S primed. Alice shot out her light signal from the origin at t equals 0, and Bob sent out his light signal at the point Q. But those two light signals arrived at Charlie at the same instant of time. Therefore, in the moving reference frame, those two events would be judged to be simultaneous events. Indeed, there's nothing special about the point Q. We could have said that Alice and Bob were separated by any distance 2d. D can be anything. Therefore, simultaneous events arise along the whole green line, ct is equal to v over c times x. So let's redraw the diagram with what we found. In the rest frame S, which has these black axes here, x and ct, we see that vertical lines connect points at the same position. These are lines parallel to the t-axis, which of course arises at x equals 0. Whereas horizontal lines connect points at the same time. These are lines that are parallel to the x-axis, which arises at ct equals 0. So what about the moving frame of reference, S primed? This is Charlie's frame of reference. In our primed reference frame, the axes would be x primed and ct primed. Where are these on our diagram? Well, as we argued before, in the moving frame of reference, Charlie is at the centre, or the origin, of his coordinate system for all times. So x is equal to vt means x primed is equal to 0. That is the centre of his coordinate system. So lines parallel to this axis, lines parallel to x primed equals 0, connect events at the same position in the moving frame S primed. What about lines that connect simultaneous events in the moving frame? Well, on the previous slide, we learned that this blue line here, parameterized by the equation ct is equal to v upon c times x, connect simultaneous events. So lines parallel to this one will be lines connecting simultaneous events in the moving frame S primed. So we call that the t primed equals 0 axis. Lines parallel to t primed equals 0, by definition, connect events at the same time. Therefore, we've learnt that this expression, ct is equal to v upon cx, is equivalent to ct primed is equal to 0. In the rest frame S, lines connecting events at the same position are parallel to x is equal to vt. But let me write that in a slightly different way. I'll say that instead of x equals vt, let's say that it is x is equal to v upon c times ct, because in this way we can use the x and ct axes. Whereas events that occur at the same time in reference frame S primed followed the line ct is equal to v upon c times x in reference frame S. So you see there's a nice symmetry between these two expressions. Likewise, on the diagram, we see that the line ct equals v upon c times x is related symmetrically to the line x is equal to v upon c times ct, which is this line. They're basically a reflection around this diagonal light ray x equals ct. What I mean is that this angle here, theta, whatever it might be, is the same as this angle here, theta, on the diagram. The axes x primed is equal to 0 and t primed is equal to 0 are related to each other via a reflection around the light ray x equals ct. Simultaneous events are parallel to t primed is equal to 0. Events at the same position are parallel to x primed is equal to 0. That's actually the definition of those axes. What we now know, however, is what x primed is equal to 0 means in terms of x and t. We know what t primed is equal to 0 means in terms of x and t. Clocks synchronized according to Einstein's procedure in the moving frame show the same time along lines parallel to ct is equal to v upon cx. In the rest frame S, we have a ct axis and an x axis. The ct axis means x is equal to 0. It's the line along x equals 0. Whereas the x-axis means the line with common ct is equal to 0. We've just learnt that in the primed reference frame, we have another pair of axes. X primed is equal to 0 is this line here. It's the one with x is equal to vt. Whereas the t primed equals 0 axis is this one. So what does the space actually look like in the primed reference frame? If the axes here are squished up a bit, what does the space look like? In the moving frame of reference, we can count our meters. We say this is the line x primed is equal to 0, and 1 meter in front of us is the line x primed is equal to 1, which is a line parallel to x primed is equal to 0. Likewise, x primed is equal to 2 is another meter ahead, x primed equals 3 is 3 meters ahead of the x primed equals 0 line, and so on. So these are lines connecting points at the same position in the primed reference frame. Likewise, lines parallel to t primed is equal to 0 occur at the same time in the moving reference frame. So 1 second later, I have this line, ct primed is equal to 1, and then 2 seconds later, ct primed is equal to 2, and so on. So you can see by this lattice of blue lines what the space looks like in the primed reference frame. It gets all squashed up. Instead of being a checkerboard of vertical and horizontal lines, as we'd have for the rest frame S, in the moving frame S primed, we have these slanted lines. So in the rest frame S, we have a coordinate system of horizontal and vertical lines. X is equal to 1, x is equal to 2, and so on. We can count in meters. Likewise, we can count ct is equal to 1, ct is equal to 2, ct equals 3, and so on, as the horizontal lines. In the moving frame, we get a different story. We have these slanted axes. But the important thing is I can still count meters in the moving frame, x primed is equal to 0, 1, 2, 3, and so on. And I can still count time, ct primed is equal to 0, 1, 2, 3, and so on. We can also see from these diagrams what happens if our observer moves more quickly. Remember that x primed is equal to 0 means x is equal to v upon c times ct, whereas ct primed is equal to 0, of course, means ct is equal to v upon c times x. As I mentioned before, this angle here, theta, is the same as this angle here, theta. So if I increase the velocity v, then these lines get squished up closer towards the light ray. So if I increase the velocity, I get axes that look more like this. The axes approach progressively the light ray x is equal to ct. This means that the space-time becomes ever more compressed as we go to faster and faster speeds. Indeed, as the velocity of the observer approaches the speed of light, the axes fall onto the light ray, x primed is equal to 0, and ct primed is equal to 0, both fall onto the light ray, x is equal to ct. In some sense, this means the entirety of space-time for an observer moving at the speed of light compresses to this single line in the diagram. But since the axes describe lines of simultaneous events and lines connecting events that occur at the same position, for an observer moving at the speed of light, all events occur at the same position and, in some sense, at the same time. Of course, this is kind of a pathological point. It's a limiting scenario where the observer is approaching the speed of light. In practice, we'll see that can never really happen. But if we're talking about a photon, for example, that really does move at the speed of light, then, according to this analysis, time really stands still. and in some sense, everything is really occurring at the same position. It's a very crazy notion of space and time. So all of this is a profound discovery. It indicates the breakdown of the concepts of a universal time and simultaneity. Whether two events occur simultaneously or not depends on your reference frame. Of course, now we want to go further. Having understood these important concepts, we actually want to derive the transformation between the reference frame S and the reference frame S primed. We know the Galilean transformation for this, but we've seen that that contravenes the concept of the constant speed of light in all inertial reference frames. So what is the correct transformation between the static or rest frame S and the moving frame of reference S primed? Well, of course, these are the famous Lorentz transformations, and Einstein was able to derive them using very simple arguments. And that's what we'll cover now. The question is, what is the coordinate transformation that takes us from x and t to x primed and t primed? That is, how do we go from the rest frame S to the moving frame S primed? Well, we know that x primed is equal to 0 is the same as x is equal to vt. What I mean is that when x is equal to vt, this is the origin of the moving frame S primed. On the other hand, we know that when ct primed is equal to 0, this is the same as ct is equal to v upon c times x. Namely, along that line, we have events occurring at the same time, t primed is equal to 0. So how do we relate x primed and x? How do we relate t primed and t? The most general form is to say that x primed is equal to x minus vt times some function of the relative velocity v. This is the most general form because when x is equal to vt on the right-hand side here, we have x primed is equal to 0, exactly as we want. But I still don't know what this function f of v is. Likewise, if we look at the second condition here, we see something similar. I can write that ct primed is equal to ct minus v upon c times x into some, in general, other function, g of v, some function of the relative velocity g of v. Again, this works because if I look at this expression here, when I set ct is equal to v upon c times x, then indeed that corresponds to ct primed is equal to 0 independently of the function g of v. So I have two expressions here which connect x primed and t primed to x and t. But I also have two functions, f of v and g of v, and I don't know what they are. Einstein made progress here by utilizing both of the postulates. One of the postulates is the constant speed of light in all reference frames. What this means is that a light ray in reference frame S will have the same speed as a light ray in reference frame S primed. Therefore, I can write for a light ray that x is equal to ct in reference frame S, whereas x primed is equal to ct primed with the same speed c in reference frame S primed. Bear in mind that this is for a light ray. How can I use this information? Well, let's take this expression from number 2. Write it out again. Ct primed is equal to ct minus v upon c times x into g of v. And now I will utilize this expression to replace ct primed by x primed. I can therefore say that on the left-hand side here, this is actually equal to x primed. I can also use x is equal to ct for the light ray to convert the ct here to an x and the x to a ct. So I'm basically swapping everything around. So what does this give us? We get that x primed is equal to x minus, and then if I just do some tidying up of the algebra here, cancelling those c's, I find that that's x minus vt times g of v. But we already have an expression for x primed from condition number 1, and there we learnt that x primed was x minus vt times f of v. Here we've derived it for a light ray, and we find that x primed is x minus vt times g of v. And of course the conclusion from this is that the functions f of v and g of v are actually the same. So this has reduced the complexity of the problem. I now only have to find one function, the f of v. To determine this function, we now use the principle of relativity. The idea here is to say that there is no preferred reference frame. When we talk about the rest frame and the moving frame, who's to say who's at rest? If I am moving down the x-axis with a speed plus v with respect to u, this is of course the same as you moving in the opposite direction with a speed minus v down the x-axis with respect to me. So there's no preferred rest frame. Whatever transformation I do in the forward direction must also be applicable in the backwards direction. So if I imagine two reference frames in the standard configuration, S and S primed here, with the primed reference frame moving along the positive x direction with a speed plus v, this is entirely equivalent to this situation depicted here, where reference frame S primed is static and reference frame S is moving in the opposite direction with a velocity minus v. What this tells us is that I can perform the inverse transformation just by replacing v by minus v. If I want to go from S to S primed, I use plus v. If I want to go from S primed to S, I use minus v. So once we have the forwards transformation, which I've written here, x primed and t primed in terms of x and t, we can automatically obtain the backwards transformation simply by replacing the primes by not primes and the v's by minus v's. And this property comes from the symmetry of the situation. How does this help us? Well, this second pair of equations that we've obtained here by symmetry must be consistent with literally solving this pair of simultaneous equations for x and t. So let's just take this pair of equations for x and t here and substitute into them the expressions for x primed and t primed. This will then allow us to find the function v. So we will write x is equal to x primed plus v t primed times f of v. That's just restating this expression. And now every time I see a primed coordinate, I'm going to make this substitution. So let's go ahead and do that. Instead of x primed, I write x minus vt times f of v. And then instead of t primed, I write, or ct primed, I can substitute in ct minus v over c times x, all multiplied by f of v again. All of this stuff is multiplied by f of v. So on the left-hand side, I have an expression for x. On the right-hand side, I just made these two substitutions for x primed and ct primed. Does this make sense? Well, on the left-hand side, we just have an x, we don't have any t's, so we should not have any t dependence on the right-hand side. We see that that actually works out properly, because here we have minus vt times f, and here we have plus vt times f. The c's cancel. So this is a good sanity check. There's no time dependence on the right-hand side. Let's tidy up the remaining terms, and it's straightforward to show I get the following. There's a common factor of x in these terms, and there's a common factor of f of v squared. There's an f here in both terms, and also this f outside the brackets. Then what's left is 1 minus v upon c squared. So this is a strange equation. On the left-hand side we have x, on the right-hand side we have x f squared into 1 minus v upon c squared. But of course x is just equal to x, and therefore this tells us that this quantity f squared of v multiplied by 1 minus v upon c squared must be equal to 1. And that allows us to extract the function f of v as 1 over the square root of 1 minus v upon c squared. And there we have it. We've managed to find the function f of v that defines the transformations. If you're worried here that we took the positive square root when determining the function f, and maybe you're wondering what happens if we take the negative, we always take the positive because at v is equal to 0, x primed should equal x. So that property that the two reference frames are the same when v is equal to 0 implies that we had to take the positive square root here. Okay, so we've determined the function f. Let's now write out the full transformation equations. These are the so-called Lorentz transformations. They tell us how to go from x and t to x primed and t primed due to a relative velocity between the reference frames along the x direction. These coordinate transformations between different inertial reference frames were derived purely from Einstein's postulates. And we see something very profound here, that space and time get scrambled up. We see that t primed, the time in the primed reference frame, depends not just on the time in the unprimed reference frame, but also your position. This implies the breakdown of simultaneity at a distance. It tells you that time is relative and actually depends on your spatial coordinate. Now here, we only considered motion along the x direction, and it's very straightforward to show that the y-coordinate is not affected, and the z-coordinate is not affected. The Lorentz transformation for a relative motion along the x direction scrambles up x and t with x primed and t primed, leaving y and z unchanged. This is referred to as being a Lorentz boost along x. Of course, we could have a relative motion along some arbitrary direction, and that's trivially obtained simply by a rotation of our coordinate system. That can be done post hoc once we know the Lorentz transformations along x, but in this lecture course we're just going to consider the so-called standard configuration, where we consider a relative motion along x only. That's without loss of generality, it's just for simplicity. These transformations are often written in a more concise way, using the Lorentz factor gamma, which is precisely this function f of v that we've just worked out, namely 1 over the square root of 1 minus v upon c squared, and also this parameter beta, which is exactly just v upon c. It's the ratio of the relative velocity to the speed of light. This is the thing that really controls relativistic effects. So gamma itself can be written as 1 minus beta squared to the power of minus a half. Using these definitions, I can write the Lorentz transformations more concisely as simply gamma into x minus beta ct and gamma into ct minus beta x. Of course, y and z remain unchanged. So here we see the kind of pleasing symmetry between space and time. Both expressions have this Lorentz factor gamma. In this expression, we have x minus beta ct, whereas this expression we have ct minus beta x. To see the symmetry between space and time, we really have to choose the units in which the speed of light is equal to 1. I'm always writing everywhere in these equations c times t, rather than just t itself. In that way, we see that the x and ct are exchanged in these two expressions. X appearing in this expression appears here in this expression. Ct here appears down here in this expression. So here I've written out the Lorentz transformations that we've just derived. These tell us how, when we have x and t, we can go to x primed and t primed. But what about the inverse transformations? How would I relate x and t to x primed and t primed? Well, I could, of course, just solve these equations simultaneously and rearrange them for x and t. You can do that, but actually there's a much easier way, which we already exploited to derive these transformations. Namely, we can use the symmetry of the situation, the idea that there is no preferred rest frame. In that case, I can simply replace the primed reference frame by the unprimed reference frame by switching the velocity from v to minus v. If I change the sign of v, I change the sign of beta. But notice the gamma factor remains unchanged because it only involves beta squared. So a change in the sign of the velocity does not change the gamma factor, it just changes the beta. So very straightforwardly, I can utilize this to write down the inverse Lorentz transformations. They are that Ct is equal to gamma times Ct primed plus beta x primed, whereas x is equal to gamma into x primed plus beta Ct primed. As before, y is equal to y primed and z is equal to z primed. These are the inverse Lorentz transformations. I obtain them very simply by replacing the primes by not primes in these expressions, and the beta by minus beta. We began this discussion by considering how Maxwell's equations predict light propagation in a vacuum with a universal speed of light, c, which is given by a collection of fundamental constants describing respectively electric phenomena and magnetic phenomena. Manifestly, these equations are not invariant to the Galilean transformation, and that's because we have a single fixed speed of light in all inertial reference frames, whereas the Galilean transformation tells us that we simply add or subtract velocities when we go to different reference frames. But Maxwell's equations are invariant to the Lorentz transformations that we've just derived. What this means is that if I transform from x and t to x primed and t primed using the Lorentz transformation rather than the Galilean transformation, then the form of these wave equations will remain exactly the same, importantly, with the same speed of light. And of course, this is consistent with Einstein's postulates. This is fairly easy to show. I suggest you have a go at it yourself. Finally, I want to consider the so-called non-relativistic limit. The non-relativistic limit corresponds to v much, much less than c. Here, we should really not observe many relativistic effects. Why? Because this corresponds to the usual classical physics of Newton and Galileo, which actually works very, very, very accurately in that regime. Relativistic effects only become important when we have velocities, relative velocities, that are very, very large compared with the speed of light. So this condition, v much, much less than c, another way of putting that is that beta is much, much less than 1. Remember, beta here is exactly the ratio v over c. So if relativistic effects are weak in this limit, we should be able to see that the Lorentz transformations reduce to the usual Galilean transformations. So let's see that that happens. Let me write again the Lorentz transformations. We have that Ct primed is equal to gamma into Ct minus beta x. X primed is equal to gamma into x minus beta Ct. Y primed is equal to y. Z primed is equal to z, because we're considering a Lorentz boost along x. Just to remind you, beta is v upon c, and gamma is 1 minus beta squared to the minus a half. That's the Lorentz factor. So let's consider the situation when we're in the non-relativistic limit. Let's choose v is 300 meters per second. That's the speed of sound. This gives us a beta of 3 times 10 to the 2 divided by 3 times 10 to the 8, a beta factor of actually 10 to the minus 6. So you can see that even when we're moving rather quickly with the speed of sound, the beta is actually very, very small, 10 to the minus 6. The gamma factor is then very, very close to 1. and that's accurate to 1 part in 10 to the 12, it basically involves, as you can see here, beta squared, and if beta is 10 to the minus 6, then the gamma factor is basically 1 to an error of 10 to the minus 12, which we can really ignore. We can actually be more quantitative than that by doing a Taylor series expansion in the small parameter beta, and that gives us that gamma is equal to 1 plus 1/2 of beta squared plus terms of order beta to the 4. So you can see really here where that error of 10 to the minus 12 comes from is because we have a correction here of order beta squared. So the punchline is, if we go to non-relativistic speeds, we can really replace gamma by 1. Okay, so what happens when I take beta to be something very small and gamma to be something very close to 1? We'll take Lorentz transformations, which I've written here, LT for short, and we'll use gamma as 1 and beta is very small. The first equation, CT primed, goes to CT minus beta x, but beta is very, very small, so we can neglect the term beta x. X primed goes to x minus beta ct. Here it's not quite so simple because we have beta times c. Beta times c is the velocity v, which is not vanishingly small, and so I can write that as minus vt. And obviously y and z remain unchanged. Cancelling a factor of c in the top expression, we obtain the notion of the universal time, and of course these expressions are precisely the Galilean transformations. So indeed it is correct that when we go to the non-relativistic limit of speeds much less than the speed of light, the Lorentz transformations reduce to the Galilean transformations, as we knew they must. So in the next lecture, we'll be exploring the consequences in the implications of these Lorentz transformations.